All right, let me get used to this. All right, so first I'd like to thank the organizers, okay, Simon and Michael for inviting me to come to this meeting. Okay, it's great to see a lot of old friends. I haven't been traveling to Europe that much since pandemic. Okay, and also this whole generation young student now getting excited by this the progress, great progress in cold molecules. Okay, yeah, I it's fantastic seeing so much great results. I'm going to share with you a few kind of experiment we're working on. Okay, also on this on molecules. Okay, and this let me see, get oh, I got it. Okay, cool, and that's my title. Okay, so for the first part, I'm going to talk about this non-dipolar molecules, and this you can still condense them, and what other things we can do. Hey, including the both enhancement of reactions and met with phase matching, phase doubling, and entanglement generation. And I was too ambitious. I'm hoping to also cover a little bit about this the other differences, and this will be dipolar okay, system. But I think I'd rather kind of more focus on the first topic. Probably just briefly mention about second one, but I'll have a little bit time. All right. So starting from the time when I was a postdoc in Innsbruck, okay, and I had a great fun looking into the production of molecule based on atomic BEC, okay, and it was everything was amazing in the year 2003. I think the entire field just excited, just like what happened in the past year and so on. People suddenly realize how to convert atom into molecules near the base bar resonance. So you can see in just in 1 year in 2003, many molecules been created by many groups. Okay, and this is the one this working with Han Christoph. I think we're now kind of probably the oldest two old guys in these meetings that are still kind of thinking about well, and we are both still working on CDM. All right, what we did is that for regular atomic BEC, okay, if you just a random magnetic field across a phase bar resonance, you create molecules. All right, and in order to separate atoms from molecules, we can apply a kind of magnetic field gradient. Apply a certain magnetic field gradient, you can levitate the atoms, and then molecule will be under levitated. Or you can levitate the molecules, atom will be over levitated, and this because atom molecule different magnetic moment. All right, but we call this a molecular quantum gap, but we didn't say that's a BEC. Okay, okay, for a reason I'll briefly mention. And I think in the next couple of years, people are pushing toward kind of a lower temperature, higher density. This kind of this review probably kind of landmark, kind of separating the field. After this, people are more moving into these polar molecules, new ideas. Okay, and however, this people would realize we want to continue to go to reach a quantum degeneracy. But why didn't we do that? If you look at that paper closely, there's a 2003 science paper that we created CJ molecules. In one direction, we already showed the temperature extremely low, 2 nanokelvin. Okay, that temperature would be enough to kind of support the molecular BEC. However, the vertical direction is so much hotter. Okay, and once it gets in the thermalized, then becomes thermal gas. Okay? And another thing we didn't quite couldn't understand is that the creation for this atom to molecules near the phase bar resonance only give us about 20% conversion fraction. Okay. All right. So so after many years, this problem still kind of so, bothers me. We're trying to see what exactly we didn't do correctly, and we couldn't just bring this molecule to BEC. With the 2 nanokelvin, it certainly shows a potential. So in Z direction, become 40 nanokelvin. Okay, and later we realize this because we apply those kind of magnetic field gradient. Okay, that will lead to an inhomogeneity in the Z direction. Okay, so during the conversion process, the molecule are created with a variable different kind of this momentum. So that lead to the strong heating. So coming back to here, so you can see Okay, see in the z direction. Say in the beginning, the aspect ratio more like 3:1 or 4:1, but this molecule is certain turns out to be stretched in the z direction, become much harder. The second thing, you can also see that the molecular size is smaller, also in the this radial direction. Okay, and this is because this conversion process that depend density dependent. At the center of the trap, when the density is higher, they create more molecules. So when the molecule created, there's a mismatch. Okay, they are not created in the ground state of the trap. Okay, so actually, when you try to lead this molecule in the dipole trap for some time, they will all be hitting in all three directions. All right. So years later, then when we have better technology, better way to create kind of a better optical trap, okay, we try to create a two-dimensional trap to minimize the this spatial extent in the z direction, and also horizontally there's a no more kind of combining potential, okay, less than 1 hertz, okay, such as almost like a flat box, okay. So there's no more summarization that is required, the uniform density to begin with, and the vertical horizontal, okay, temperature can be pretty much the same, and then we pretty much repeated the experiment we did, okay, like years ago. So this time we were able to, using the same phase bar reason that we did this 20 years ago, we're able to show that this how we can convert atom into molecule that have the same temperature or even a bit lower than the initial kind of atom temperature in the same trap, and then the molecule become uniform. Okay, and this particular molecule also has a particular kind of properties, even though they are weakly bound, but they actually have a reasonable kind of lifetime. These are phase bar molecules, and partially because this CDM atom pretty strong kind of spin orbit coupling. So even though the cell there's alkali atoms, okay, there is a short range kind of this dipole repulsion, okay, and that can provide a better collision stability. All right. So, and we characterize a couple of things. For example, on the equation of state, okay, show that indeed these molecules at the lower temperature we can reach, we can get the molecular BEC. And once we know how to optimize the system, we can go back to harmonic potential. And this is one example to show this onset molecular BEC in the harmonic trap. We can see the conventional bimodal distribution. Okay. All right. So for us, what is the motivation for us to study these molecules? Okay. So okay. So I guess I need to mention about this stability, the special G-way molecules. Okay. The G-way molecules, we still have an atom in the S-way. When they collide, they couple to the particular this molecule with a large angular momentum. Okay. And because of the spin orbit coupling, we believe there is, according to calculation, the dipole-dipole interaction actually 30 or 40 times stronger than this direct magnetic dipole-dipole interaction of this electrons. Okay. Let me see. We'll do this. So another thing, really, like when you go to 2D, okay, let's compare this experiment very early, something we did, okay, almost 20 years ago. At that time, we only reached 250 nanokelvin. Okay, and later the Innsbruck group continued to push, get to lower temperature. Okay, and eventually will go down to this 11 nanokelvin. You can see the blue dashed line shows the kind of universal prediction how large the loss rate could be. Okay, but our observation show the opposite. The lower temperature we can create, the lower this molecular loss coefficient we are seeing. So almost surprised by one even close to kind of factor 30 or 40. When you go to the lowest temperature, 11 nanokelvin, and also going to going to more to the 2D gas on the right hand. So in this plot, okay, on the right hand side, the system more closer to 2D gas. On the left hand side is more closer to 3D. Okay, so the suppression of this loss compared to the unitary limit by almost factor 500. Okay, so this over the condition and explain why this phase bar molecule can be stable and can condense. All right, so now let's talk about the physics or the chemistry we can do. Okay, with this with the molecules. So we know from the general chemistry, this class we've taken. Okay, conventional thing about the collision or chemical reaction happens when particles collide. And the collision rate will depend on the density, depend on the velocity, okay, depend on the cross section. Okay, so you can introduce this parameter to characterize the reaction rate. But in the many body regime, things are different. Now we start to talk about atom preparing one quantum state, and like a couple of molecules also prepare in another quantum state. Okay, when that quantum state is populated by many particles, okay, then the interaction between these modes, these different states, is given by the wave mixing. How the atomic wave, okay, is mixed with the molecular wave, in a way similar to nonlinear optics. How the mode occupied by red photon is mixed with another mode by another photon, and then they can generate photons of new colors. So it's through 3 or 4-way mixing, nonlinear process. Okay, so given that will be the supposed the most fundamental process to model how the different modes are coupled. Okay, we can try to speculate what would be the chemistry different in the quantum many body regime. First of all, given the Hamiltonian, we can just write down the Heisenberg equation, how the molecule be created. Okay, looking at this equation, you see, well, this is kind of what you expect. The creation of molecules coming from the density. When density is higher, then you get more molecules. Okay, but then you start to see, but this is the differential equation. It's a nonlinear differential equation. There's a lot of interesting features in the nonlinear kind of this partial differential equation that we learn in mathematics. First of all, because this is interaction supposed to be Hermitian, there is a process going from one side atom to molecule, and also a molecule back to atoms. In principle, should be a kind of Hermitian process or Hermitian operator. Second, because the nonlinear process, okay, this the phase will come in the interesting way. Okay, like right here you can see you have phase of the molecule dagger, so and the phase of the atom square. Okay, so it should be a coherent process, and it depends on this phase of the atom molecules. And also because this is a nonlinear process, so it's been predicted. Okay, so the coupling strength here with nonlinear depends on this population. The more atom molecule you have, the faster reaction will occur. Okay, this is called the super radiance, or you can say this is stimulated, and the people also call it this kind of super chemistry. All right, so let's skip this. Okay, so this and this is a prediction. Okay, what would this nonlinear differential equation would lead to the creation of atom molecules? Okay. So starting from 100% atom, the prediction is that there's if you do the mean field calculation, you'll see your atom can be converted. This assuming you have bring the molecule two state into degeneracy, 100% atom to begin with, and how many molecules can be created. So you can see certainly this mean field and the exact diagonalization, they give you very different kind of behavior. And eventually there seem to be some, if you follow the exact quantum calculation, it looks like system will settle, even though you do not introduce any kind of dissipation and so on. Okay, there is some kind of damping, okay, oscillation and damping occurring, okay, in this quantum model. And this is kind of close to what we see. In our experiment that we started atomic BEC and jump to resonance, and then you can see a fast quench of a population in the atoms, and followed by this molecule number increases, and then you can see these oscillations. Okay, and this from a previous one, I'll just go quickly to draw this kind of the conclusion. While we see this oscillation frequency based on the sample exactly on resonance between the two state into degeneracy, we see this oscillation frequency indeed depends on the population. Okay, and depends. And if you look at the oscillation frequencies, okay, as a function of atom number, initial atom number, okay, we can compare that with the different model. Okay, first based on two-body couple, our naive phase bar coupling model, and also compare with a three-body model, okay, where the creation molecule more coming from the recombination process, 3 atoms come together, and scatter into one atom and also one molecule. Okay. From our data, this is how we show that likely the creation of this molecule near the continuum actually dominated by three-body process, which now we had a better understanding. This is possible when there's a large population in this ground state, because in this case, each field operator can be replaced by square root n. Okay, so therefore, the more population, more atom you have, then the three-body process will be enhanced. Okay, so now let me move on to the more recent work. This is something we just put on the archive this couple of weeks ago. Okay, so another important feature, this kind of nonlinear wave mixing, is something we can learn from our kind of experience in this quantum optics. When we in the quantum optics, you can try to also have generate. You also have a nonlinear wave mixing process when you set ray photons into a nonlinear crystal. All right, when the intensity of light is strong enough, then there's a small fraction of the light can be converted into the blue photon. Okay, and this is possible because the nonlinear process, two red photon can be kind of mixed and converted into a blue photon when the system at this so-called second order susceptibility. Now, similarly, for atoms also boson here. Okay, so if you also prepare atom in the same state, then it's just like this red photon, light photon in the same mode. Okay, in the presence of strong sufficient population in the mode, now there's also enhanced probability that you can convert these red photons, in our case atoms, into molecules. And in terms of if you write down in terms of this field operator, these two processes are described by exactly the same process, the same interaction Hamiltonian. Okay, and the important kind of prediction of this is that this process you can create this molecule this way, okay, atomic wave converted into molecular wave. The phase of the molecule should all be a factor 2 larger than the phase of the atoms. This is so-called phase matching condition, or you can see this phase doubling. Okay, that happens for photon is clear. The frequency of the blue photon should be 2 times the frequency of the red photon. Okay, so how do we design experiment to test this conjecture? So let's consider the BEC, okay, and then we can imprint the phase on the only on only one side, say on the right hand side. Now I compare them. Okay, if that prediction is right, then the relative phase should differ by 2 phi. Okay, so that's the idea. But instead of just cut the BEC into 2 halves, okay, we try to do a trick. We try to apply a standing wave, okay, which which can modulate the phase at a shorter length scale. Okay, that allows us to kind of see the stronger kind of phase modulation over kind of unit distance. Okay. All right, so our experiment, we design an experiment like this. Starting with atomic BEC, this blue circle is a atomic wave function, and then we apply this standing waves. Okay. And that will leave a kind of phase modulation on the atomic BEC. After that, we pair them and see how much the molecule is modulated. Okay, so we do the third round experiment just to show that we can show the atomic BEC, molecular BEC can be diffracted by the standing wave. You can do in the so-called capacitor-derived diffraction. That's when the BEC illuminated by 2 laser beams with the same frequency, and that will support a stationary lattice. In this case, okay, any particle, doesn't matter, atom, molecules, okay, or can be transferred to 2 times the recoil momentum. Okay, to absorb a photon from the left beam and emit a photon into the right beam. Okay, then it will go to the right, or the other way, you can go to the left. So you can see atom can be diffracted to positive position and negative position. The same thing on molecule. The molecule also diffracted in the positive direction, negative direction, but you can see the displacement is a factor 2 smaller. That's because molecule has twice its mass. Okay, right. We can also do the so-called kind of Bragg diffraction. If you apply the 2 laser beam with slightly different frequency, you can induce a resonant kind of this Bragg diffraction. in this case, the system is more like a kind of spinner. Okay, zero. Okay, the zero momentum can then spin down, and coupled to this 2H bar K can be spin up. Okay, so you can see the Rabi oscillation between zero momentum and this 2H bar K. So this population is showing this coherent oscillation between these two momentum for atoms and also for molecules. And you can see the oscillation of a molecule is faster due to two reasons. First, one molecule have a higher polarizability because one molecule made of two atoms. So the same amount of light, you can induce twice of the light shift. Okay, and also the other thing is that we also this molecule, the recall, the detuning will be different because the molecular mass is twice as large. So you need to adjust the laser frequency difference to induce a resonant transition. Okay, so this is to show that indeed we can see this matter wave diffraction, okay, and this interference with our molecular BEC. Now try to think about our proposal. We can try to do a phase modulation on the atoms. After that, we pair them. Okay? So when perform the phase modulation on the atoms, so you can imagine this the phase will be modulated. Now we pair them. If the equation of motion of molecule really just respect this simple differential equation, then we imagine the exponent must be twice as large because it's a phi a square on right hand side phi a square. Okay, and how do we determine? So and this how do we know about determine this the phase modulation? Now, from a diffraction experiment, we can also rewrite the wave function in terms of the population or the amplitude in the zero momentum state here. And amplitude is the 2H bar K here. Okay, so this is essentially we can show the intersuperposition of two states. Some atom will have a zero momentum, some atom that will be original BEC, some atom with a 2H bar K finite momentum. Okay. But when you pair them into molecules, then you have three possibilities. You have now you take this whole thing square, take the phi a square. Okay, now you're going to have three terms. You have a two atom with the same zero momentum can pair into molecule with zero momentum, or two atom with a momentum 2H bar K, and then you could create a molecule 4H bar K. Or you can also have the cross term. That's the atom with zero momentum can pair with atom with 2H bar K. And this is not the second harmonic generation anymore because they are coming from atom in different modes. Okay, in the nonlinear optics, this is called some frequency generation. Okay, so I put a different coupling strength gamma prom. But there's a factor 2 because the cross term phi 0, phi 2 is the same as phi 2, phi 0. And this is due to the this bosonic symmetrization. Okay, because these atoms are bosons. So with this this expectation, you will expect the molecular population will depend on this. Okay, if you take this in square, this is a molecular population in the zero momentum state. The term in the middle will show you the population in this 2H bar K. And the last term will be the population of molecule with 4H bar K. And you can also see right here, the molecular population essentially tell you the second order correlation function of the atoms in the phi 0 and phi 2. So these are all theories. So what do we see in the experiment? In the experiment, you see on the atom, again, we apply this simple kind of Rabi oscillation between the two states. Okay, zero momentum, that's a red one. 2H bar K is a blue one. And then the oscillate just like cosine square and the sine square, where big omega are linked to the Rabi frequency. Now, for molecules, because now there are three possibilities. Indeed, a molecule you see three possibilities, 0, 2, and 4. Okay, so now indeed I see three possible outcomes. And I mentioned this for molecule with zero momentum, atom with zero momentum, it can give you molecule with zero momentum. So cosine squared becomes cosine 4. Sine squared becomes sine 4. But then the term in the middle, that is the interference term. Interference term, yes, a non-trivial kind of amplitude that we need to do experiment to determine this turn out to be 0.58. And this will be important for the later entanglement kind of evaluation. But right here, just show that indeed we have a good model. We can see how the population of atoms, molecules in three different momentum modes, oscillating with time. Okay. All right. With this knowledge, we can we can determine the phase. Okay, so okay, let me go back to the math. Okay, how do we determine the phase? You see, you can equate these two equations, so you know how to determine how much the phase is modulated. Okay, you also equate these two equations, you see how much the phase of the molecule is modulated. Okay, so this is the final result. In the y direction, we show how much for any image, okay, a molecule, we can determine how much the phase of molecule is the phase modulated molecules. Horizontal axis is the phase of the atoms. Okay, so we do the phase imprinting, and then we see how much the phase of molecule is modulated. And these are the formula. We can use a population we see on the molecule, population on the atoms, to determine the kind of relationship between the phase on the molecule atoms. Okay, and this is residual. Okay, as compared to the slope, you fit it the slope essentially too. Okay, and if you can check out our this paper, there's a tiny residual at a level about 4 or 5%. Okay, that's due to the different strength of a second harmonic generation and some frequency generation. Lastly, this pairing also lead to some non-trivial generation entanglement that we didn't expect when we first performed the experiment. Okay, and when two atoms are paired, okay, what we see is that the molecule will be distributed into these three states. But such kind of superposition cannot be modeled based on any classical combination. So one way to show this the molecular state is not a product state of atoms. We can evaluate so-called separability. Okay, in this case, it turns out to be the molecular population subtracted by the molecular population in the 2H bar K and the molecular in the 4H bar K, and this classically limit between 0 and 1. But our experiment data, it shows I can go below 0 and not become non-separable. Okay, so but let me provide a kind of more kind of a intuition what's happening here. Think about your two coins. Each one of them can be 0 or 1, and each of them can be, say, 50%. Okay, classically, the probability to get 0, 0 and the probability to get 1, 1, subtractive the probability 0, 1, and 1, 0 can never be less than 0. Okay, so if your equal probability, you're going to have a 25% for P00, 25% for 0, 1, 25% 1, 0, 25% 1, 1. That at least will be 0 or larger. Okay. But what we see, because of both symmetrization and the interference term enhance so much, it go beyond the classical bound. Okay. So when this drop below 0, even though just a little bit, it shows that this process by itself generates some level of entanglement. And then we can see what kind of entanglement in general we can try to evaluate the so-called entanglement weakness that quickly show the result. These are 4 weakness, okay, and one of them can go above 1. That shows the system is no longer is closer to such particular entangled state, Bell state, and that's at least the result here. Okay, our state, okay, when we did this weakness W5 plus. That's this blue one is higher than 0. The system closer to this particular Bell state. And 5 plus is 0, 1 plus 1, 0. It's is closer to this state. Not 100% in this Bell state, but it's closer. All right. I think because my time's done, I'm just going to summarize this part. So try to show this is the creation of molecular beads in our case in this coherent process. When there's a phase modulation on the atom, we see twice the modulation on the molecules. In addition, we show that this creation process lead to the entanglement. I have to emphasize not the entanglement of molecules, is the molecular state itself is an entangled state of 2 atoms. Okay, and we provided our evidence and also our this picture to understand how the molecule entangled in this situation. All right, I think I'm just going to stop here. Thank you for your attention.
Thanks so much for a wonderful talk. Are there questions? Actually, I had a burning question on the entanglement.
Yes.
If I consider these just as waves, like the atoms and the molecules as waves, and then I have a nonlinear process that creates them, I would find precisely what what you did, and
Mhm.
would therefore the interpretation of the non-classicality, I mean, that would apply to
Mhm.
waves if
Yeah.
you were
Yes.
to go
Mhm.
through with the
Mhm.
reasoning, right? So it's basically, you could also say it's a demonstration of the wave-like nature
That's right.
of the
Right.
atoms and molecules.
But this, but it becomes entanglement because you try to assign the wave as the wave function of a single particle.
Yeah.
Okay. So when one molecule is created, now it turns out they have a much higher probability to be 0, 1 plus 1, 0 than others.
Yeah.
Okay. If for classical way, any way they're all made of many particles, then you wouldn't call this kind of entanglement of classical waves.
Right. But would that mean that one would have to have sort of some single atom resolution or something to actually use that entanglement?
I guess in our case, any molecule, because all the molecules are prepared in the same state. So essentially, all these molecules, they are in the superposition of these 3 states, and this state itself is not a product state of 2 independent atoms.
Also, a burning question on what was coming after that part of your talk.
I'll just maybe briefly mention very quickly. So we look into this Bose-Fermi mixture, okay, and we are trying to mix this. Maybe just show 2 slides. There are 2 kind of a limit people think about how this mixture can lead to this effective interaction. In the case of heavy boson with light fermion, okay, these are heavy boson embedding light fermion. One picture is coming from condensed matter. That is a fermion mediate interaction between 2 bosons. Okay, the other picture near the resonance, there's an ephemeral potential. The fermion actually lead to a 3-body bound state. Okay, so we did a bunch of study in the crossover regime and so on, and maybe I just come to the conclusion right here. We show that when the mediate interaction gets stronger and stronger, at some point it starts to support one bound state. But this bound state is a 2-body bound state. And then you need to go even stronger when you get very near the resonance, then the ephemeral resonance will appear. So ephemeral resonance in the thermal gas is a 3-body process, but in the quantum gas, it seems to be broken down into 2 steps. First is a fermion pair 2 cesium atoms into a 2-body bound state, and then later that cesium dimer bound state combined with the lithium become the 3-body bound state. So this is our current hypothesis that seems to be implied by our measurement in the crossover regime. Okay, and that will kind of also bridge these 2 limits under this RKKY limit and also this ephemeral limit.
Beautiful. Yeah.
Yeah. Mm-hmm.
I have 10 more questions. For example, I was wondering
Yes.
about when you make the molecules, it's a sudden measurement of the G2 correlation function of the atoms.
Mm-hmm.
So now by tuning somehow, for example, if you did an RF experiment to associate the molecules at a given scattering length, you might be measuring the G2 correlation function at very short distances given by the scattering length, maybe. And that would be cool. I don't know.
Yes.
Is that
okay? So I think if you try to do the association away from resonance,
yeah.
Okay, but maybe use a radio frequency or something like that. I think that will work, but maybe that would also just reflect the probability kind of contact. Okay, probability.
Yes, it would always measure the contact times.
Okay.
The rest. Yeah.
Mm-hmm.
So, cool. All right. If there are no more questions, then let's thank Cheng. All right.